Hi, in this video, I'll be going through more applications of differentiation and going through some concepts about directional derivatives now. So, what we know that the partial x and the partial y is the derivative with respect to the x and y direction. But now we want to take a random direction with a unit vector u and an initial point starting from AB. So we want to find the equation of tangent line parallel to u, and so what we need to do is we need to cut the surface with a plane in the direction of u1 u2, and then we define the total derivative now as the natural definition as the limit of a plus a change in the u1 plus a b plus the change in u2 by a factor of h, then minus f if ab over h, and we take this as the limit goes of h goes to 0. And we can clearly see if the u is the direction of x, then we see that it recovers our original notions that we have studied, that it will be the partial derivative with respect to x, and if it's 0, 1, then it's the partial derivative with respect to y. And we also like to remember we said that if these two exist, it doesn't mean that the total derivative exists. And so it is also the similar case if f may not be differentiable even if all the directional derivative exists. And we really need all these directional derivatives to be continuous. And once you have the total derivative and you want to evaluate it at the vector u, then we know that the directional derivative is this following. It will just equals to the total derivative dot u. So it will be this formula, fx times u1 plus fy times u2. And really, the reason for that is because if we let our g equals to f of a plus u1h comma b plus u2h, then the directional derivative with respect to u will equals to this following, and this is just the limit of gh minus g not over h as h approaches 0, and this is the definition of the derivative of g evaluated at 0. And so now we let our x equals to this and y equals to that. By the chain rule, we know that the derivative equals to fx times u1, because you differentiate this with respect to h, will be u1, and we differentiate this with respect to y will be u2, and so you just need to multiply them and you get the following. And so you can also think of it as the dot product with the part fx over fy dot u1 over u2. So you can think of it as a dot product, or you can just write out the linear form over here. And so we take a look at this exercise. So f equals to x cubed minus 3xy plus y squared. So we want to find the directional derivative at 1, 2 with respect to u. And we know u is the angle of pi over 6. So the unit vector will be cosine pi over 6, comma sine pi over 6. So the partial x will be this, and the partial y will be minus 3x plus 8y. You just need to take the partial operator on f, and evaluated at 1, 2 is minus 3 and 13 respectively. Therefore, the duf at 1, 2 will be minus 3, 13 dot cosine pi over 6 sine pi over 6, and you get this as the following result. And with this idea of directional derivative, we get to know what is a gradient vector. And really, we say that the linear map can be now written as the fx fy dot u1 u2, and we know this is the direction. So we say this part will be known as, we define it to be the gradient vector of f. So the gradient vector of f will just be a vector with coordinates of fx and fy respectively in two variables, and in multiple variables it will be just fx, fy, and fz or more. So with this notion, we see that we can now write the directional derivative equals to the gradient vector dot u. So analogously, what does it mean to be a direction vector in three variables? We have the similar limit definition, and we see that it will just recover our gradient vector to be the following. And so this formula of the gradient vector dot u works for any function with more than two variables as well. And now we'll give a geometric interpretation of this gradient vector, and really it is saying that one geometric possible interpretation is that this gradient vector is always orthogonal to the level set of a function that you want. And so for example, we let f be a differentiable function and ab be a point in R2. So we know that if the gradient vector does not equal to the zero vector, then we want to say that it is orthogonal to the level curve. And what does it mean to be the level curve? Well, f you know is some function. We just need to take a level curve and project it down to xy plane. So these are the level curve. And if we have point AB on the level curve, then the gradient vector, if you draw a tangential line on this curve, the gradient vector will be perpendicular. And the proof follows because we just let this be the level curve, f of AB equals to k. And this, now we parameterize the points on this level curve with x and yt. So if we differentiate with respect to t, then the right hand side of k will equal to 0 because it's a constant. And the left hand side, you just use the chain rule, we get the following over here. And we know that this can just be interpreted as fx fy dot x prime t y prime t. And x prime t y prime t is the tangent vector. And this is the gradient vector. And so the gradient vector is always perpendicular to the tangent vector. And so it means that it is perpendicular to the entire level curve. So I hope this gives you a geometric interpretation of what is the direction of the gradient vector. And with that, we are able to calculate the tangent line to the level curve easily now. Because if, let's say we have we will just take an example to illustrate our point. We know that we want to find the equation of the tangent line to this ellipse. We can just take this ellipse to be the level curve of this function equals to 2. And so the gradient vector will equals to the following. You just differentiate with respect to x, evaluate it at -2, 1. Then you bracket. That will be the I component, and then evaluate it with respect to y, and that will be the j component. And really, because this gradient vector is non-zero, then the tangent vector will just be a vector that makes this, with dot with this, will equals to 0. And really, you can just take the reverse of this. Like, you just need to reverse it and change the sign accordingly. And you get that the tangent vector will be -1, 2. And so you just need to, we know that the gradient will now be m equals to 2. So this gives you the tangent vector of the ellipse quickly. So I hope this is clear, and you can really look through this video again if it's if you need more understanding. Moving on now is if you want to do it in 3 variables, you can also do it in 3 variables. And it is a very analogous statement. And so let's say we want to calculate the tangent plane to this epicoloid. Then you just let the function be this left hand side, and this will just be the 3-level surface of the function. So we just need to find the gradient vector, and it will just be differentiated with x, y, and z respectively, and you get the following. And then you evaluate it at -2, 1, and -3, and you get this as the normal gradient vector. And because we know the gradient vector is perpendicular, this is actually just the normal vector. And so the equation of the tangent plane will just be -x plus 2y minus 2/3z, and the other right hand side will be evaluated at the point to get 6. And you're done. So it's a very mechanical and straightforward use of chain rules or use of differentiation to get the tangent plane or tangent line. And lastly, we see that we can also interpret the gradient vector as a direction of fastest change. And really, you think about it, is because if we differentiate it in the direction of u, and we know that u is a unit vector, then our formula over here would just be this cosine theta, where theta is the angle it makes with this u. So let's just say we have a random vector and we have a u here. So this random vector u will just be, the dot product would be this following. And if we observe this, then we see that this function is bounded between the gradient vectors. And so this rate of change with respect to u is attained at the maximum of u equals to 0 and pi respectively. Meaning that the direction of maximum rate of change will be in the direction of this vector of the gradient vector. And so the maximum rate of change, which is represented by dfp respect in the direction of u, is the magnitude of the gradient vector, and the minimum will be just in the opposite direction. And so you can just think of it as you have a unit vector here, and you want to change direction the fastest. Then you just need to go in the direction of the gradient vector. And really, you can just think of it as you have multiple level curves, and you have a direction of this curve over here. For the fastest rate of change, you just need to go at the perpendicular distance to increase from one level curve to the next. So I hope that is clear. And so when we do a question and they give us a function and they ask what's the direction of maximum rate of change, we just need to find the gradient vector, and that is the direction where it has the maximum change at a single point. And this maximum rate of change will just be the magnitude of the gradient vector from what we have stated over here. And so that's all for this video. I hope you have enjoyed this bite-sized understanding of how we use the gradient vector and its application. Feel free to like, share, and subscribe, and I'll catch you in the next video. Bye!